of this 2. So this is delta del sigma of x mu, and I interchange it delta of del tau of x mu, and I interchange this. And then we do it by parts, and so we call it I1 plus I2, and here this I1 is P times del sigma del tau times the first term, which is del tau delta x mu. Oh, and what did I do with x mu dot square? So x mu dot del tau of x mu, and this I can do by integration, using the integration by parts, d sigma d tau. Now first function into integral of second. I am doing it with respect to tau, so I leave this sigma here, and this is d tau. Now integral of first function into integral of second minus integral of differential of first into integral of second del tau x mu, and this then becomes del tau of x mu. Have I done something wrong? Wait, del sigma. Oh, this delta del x mu, but I'm missing h. This is delta x mu, and this is also delta x mu. I think now it's correct. Okay, so now, so this was delta x mu, delta x mu. Okay, so this is equal to delta x mu, and this is equal to delta x mu, and therefore what I have is, let me write down this term first. This term gives me t into integral of d sigma into minus, this is the, it is this term, and this is being evaluated at into delta x mu, delta square x mu into delta x mu, and this is what is becoming minus x double dot d sigma d tau is gone. Oh, there is one. So this is minus integral of this. I have here additional d tau. So minus d tau d sigma into this, and one more term which is the boundary term. So that term is plus t times d sigma into x mu dot delta x mu at the tau boundary. And this we would find, so there is one this term and one this term, and this term would vanish at the time boundaries. And similarly, we can just write down for the other term for the I2. For I2, I2 is delta of d tau d sigma t by 2 minus x prime square, and this is minus is here, so 2x prime delta x prime, and this we have written as delta del sigma x mu, and this we interchange, so this gives us del sigma of delta x mu. So this is your twice of x prime times del sigma of this x mu. And now we again do integration by parts, and here because of this minus sign we will have the same terms that we have here. For I1 we would have minus t times d tau now d sigma into plus x mu delta x mu, and this term which is minus of t d tau times x prime mu delta x mu, and this is the. So we had actually already done all this, but because I thought it's going to be very crucial for the entire string theory, we could recap these basics. So you see here, it is in front of us that we have one term here and we have one term here. These two terms added together equated to 0 would give us the equation of motion for our action. However, we happen to have these two terms which are the boundary terms. This is one term and this is another term. Now this term vanishes over the time boundaries, okay? Initial and final time, or t minus infinity to plus infinity. This term is going to give us 0 in any case without imposing any extra condition. And here we would like this term also to vanish. So we want to retain only this term, and we want to get rid of these two boundary terms. So this we also want to vanish, and this one can do cleverly. In case of the closed strings, it is some this value at initial point minus the same value at the so you can say at sigma equal to 0 and at sigma equal to 2pi. So they are the same and they cancel each other and they give you 0. However, for the open string, let me write down this term again here, boundary term for the, so it is plus or minus of t times d tau, and into we have this x prime mu into delta x mu. and this is over the space boundaries. This is over the space boundary. So what we want to do is, for this, we want to have two kinds of boundary conditions. One of them is called as Dirichlet boundary conditions. Here, this end x, one end is fixed at some value x0, and the other end is fixed at some value x pi. And therefore, because it's fixed, its variation is 0. So this delta x is 0. And in this particular case, the end is not fixed. It can move around. And therefore, delta x is non-zero. Here, delta x is not 0. Delta x is not 0, but therefore we additionally impose that let the space derivative of x nu vanish. Now, what is the physical implication of these conditions? The physical implication of these conditions is that here, supposing I apply Dirichlet boundary conditions at both the ends, then my string, of course, the ends of the strings would not move, but it can oscillate or it can vibrate. All right? It can either oscillate or vibrate because the ends are fixed. Here,